Okay, so hello everyone. This week's lecture segments are continuing from last week on the theme of subduction zones. And in this week, we'll be looking in more detail at subduction zone thermal structures, what controls them, and what effect the thermal environment has on metamorphism and associated dehydration processes. We'll also talk about subduction interface deformation and various seismicity patterns and seismic hazard associated with subduction zones. So to start off, last week we drew a rough sketch of a subduction zone that looked something like this, and I asked you to draw in isotherms for 1,000 degrees C as shown here, and in our case we drew in an isotherm also for 300 degrees C, but the patterns are similar to what's shown here. We discussed how those isotherms or lines of constant temperature tend to plunge steeply downward parallel to the slab due to advection of cold material downward, but also how they fairly rapidly exit the subduction interface and shoot back up the subduction zone into the upper plate lithosphere, and they're much hotter beneath the magmatic arc. So overall, subduction zones show a sort of symmetrical pattern where they're very hot in the asthenosphere away from the slab, but quite cold along the subduction interface itself. So we now have that basic picture in our minds, but in this segment, I want to give you a bit more information on how exactly we come up with these subduction thermal gradients and give you a sense for how widely they vary among active subduction zones today. So ultimately, a more precise subduction zone thermal model will look something like this. The colors correspond to temperature, with blues and purples being very cold, less than 300 degrees, and red colors being very hot, greater than 1,200 degrees. And some of the key outputs that we're interested in extracting, or the sort of reference temperatures that we extract from these thermal models, are things like the temperature of the astenospheric mantle wedge, labeled TMW, the temperature of the slab top beneath the volcanic front, labeled TVF, and the temperature of the slab top at around 50 kilometers, which would be the temperature expected beneath the deepest part of the accretionary wedge, for example. But to arrive at models like that, we need several model assumptions and initial inputs, which include the following. First, we need to input a slab geometry or dip. We can often get at this from seismic reflection data for shallow depths, seismic tomography for the deeper depths. Second, we need to know the convergence rate. These days, we get this information from GPS detectors that are now set up around most active subduction zones. For ancient subduction environments, we might infer convergence rates from seafloor magnetic anomalies and other data sets that contribute to plate reconstructions. Third, we need to know the age of the downgoing plate and its thermal profile, which we would calculate from half-space cooling, so a correlation between the age and the thermal profile and density of the downgoing slab. Recall that these two things multiplied together are the parameter known as phi. This is also referred to as the thermal parameter, which will become obvious why in a few slides. Fourth, we need to know the potential internally generated heat sources. This could include radiogenic heat, especially if the upper plate is continental in origin and it sequesters radiogenic elements. And it can also include shear heating, which will be a function of how strong the interface materials are. Fifth, and finally, and perhaps most importantly, we need to determine what's called the coupling depth, which is the depth at which we assume the mantle starts to flow rather than conducts heat rigidly. This is shown in the lower left diagram where the white arrows are defining the areas of heat advection, which of course are the slab itself, which is advecting cold material rapidly downward, but this is counteracted below the coupling depth by corner flow within the mantle wedge. So you're basically pairing advection of heat against advection of cold material beneath that depth. So once all of these input variables have been supplied or guessed or estimated, you can create these thermal models and start to assess how much they vary from subduction zone to subduction zone. So let's look first at some examples from the two different subduction zones that occupy Japan. On the left is the Honshu section in northeast Japan, where the very cold old Pacific plate is subducting quite rapidly. And on the right is the Nankai subduction zone in southwest Japan, where the very young, hot Philippine sea plate is subducting comparatively slowly. And notice that both these subduction zones have essentially the same upper plate structure. That is, it's the landmass that is Japan. So the thickness of the upper plate and the depth to the flowing mantle wedge is essentially the same at about 80 kilometers. The temperatures of the mantle wedge corner are also fairly similar at around 1150 to 1200 degrees C. They also have fairly similar slab dips, with the southwest Japan slab perhaps being a little bit shallower. But in contrast to those similarities, the slab surface at 50 kilometers and the slab surface temperatures beneath the volcanic front are very, very different. Northeast Japan shows 210 degrees at what would be the base of the accretionary wedge, compared to 510 degrees for southwest Japan. And the temperature beneath the volcanic front shows only 475 degrees in the northeast Japan case, compared to 820 degrees, extremely hot in southwest Japan. These are some additional examples of thermal models that are created in the way I showed a couple slides ago. This is just illustrating, for example, the effects of slab dip. You can see the two thermal profiles on the right for the Aleutian and Nizubanan subduction zones are for steeper slabs and different plate ages and velocities. They have some similar reference temperatures to the Japan cases on the left, but also some significant differences. If we aggregate subduction geothermal gradients globally, they look like the diagram on the left, and they exhibit some pretty diagnostic patterns. So these models are for a constant mantle wedge depth of 80 kilometers. That's what the D80 means on the bottom there. And they also assume no shear heating on the interface. And these are showing the pressure temperature trajectories for the slab down to more than 200 kilometers depth in this case. And the patterns that emerge are, firstly, along the shallow part of the profile, the pressure temperature path is very steep, showing a much greater increase in pressure than temperature. This is because the ratio of cold advection to diffusion from the upper plate is quite high. But then the PT paths shown in this middle flat section has a large increase in temperature with hardly any increase in pressure. This occurs where the slab intersects the flowing mantle wedge, and this is where heat advection can occur and can warm the slab up much more rapidly than it could in the conductive case. From there, the slope becomes fairly steep again, with small increases in temperature with increasing pressure. And this is because at this stage, the slab has reached the mantle adiabat, so there's a constant temperature with depth. In other words, temperature no longer increases as you go deeper. Pretty much all of the subduction thermal models look like this. Even if we tweak some of the parameters like shear and radiogenic heating, they're always going to show the steep part labeled 1, followed by a flat part labeled 2, where it intersects the coupling zone or the coupling depth, and then a steep part again at label 3. And it turns out these models pretty simply scale with the parameter phi that we've discussed a few times, the plate age multiplied by the convergence rate. So here's a plot of the slab surface temperature at 125 kilometers depth for 3 cases: the bottom of the oceanic crust, shown in blue, the top of the oceanic crust, shown in green, and the top of the sediment pile, shown in red. And you can see that these are all approximately linear when plotted against the x-axis, the parameter phi, convergence rate times the plate age. This suggests that phi is the primary control on subduction PT paths, whereas other parameters such as shear and radiogenic heating perhaps define the scatter. You can see quite a bit of scatter, especially for the bottom of the oceanic crust. So they define the scatter around the linear relationship, but we can think of phi as clearly the first order control. So everything I just showed you was based on modeling. And you may wonder, how do we even know whether or not these models are correct? It's important that we consider some of the ways in which we test these thermal models, in other words. And there are several attempts to do this within different disciplines, which include measuring for heat flow and comparing it to predicted heat flow from the thermal models. Some attempts to compare subduction zone seismic velocity structure to the modeled PT conditions. We can use arc magma thermobarometry and geochemical characteristics, and we can look at rocks exhumed from subduction environments. Just to show you a couple of examples, here's a comparison of the thermal model for central Japan compared to measured heat flow data from the same area. Japan has a lot of heat flow data from borehole thermal gradient and conductivity sensors. The cross-section shows a thermal model for the transect shown in green, and above it is plotted the heat flow data as small black dots. The predicted heat flow from the model is shown as the solid black line. And you can see there's rough agreement, but you can also get a sense for how messy the heat flow data actually are. They're fairly scattered. But still, this is a common way to try to test these models to see if they're at least within the right approximation. Here's a result from geochemistry where the authors used the ratio of water to cerium in melt inclusions in arc volcanic rocks as a thermometer and as a proxy for the mantle wedge temperature from which the volcanic rocks were sourced. They found this pretty nice linear correlation between rock-derived slab surface temperature and the predicted temperature from the thermal models that I showed you earlier from this paper by Syracuse. One more example, there's some work comparing thermal models to pressure temperature estimates from exhumed blue schist and eclogite facies rocks. Exhumed subduction complexes are common. The left-hand map shows their global distribution, and the right-hand image shows their pressure temperature data organized by different subduction settings. The red and purple curves on the right image are subduction zone thermal models. And so this paper actually argued, in fact, that most rocks show higher slab surface temperatures than predicted by the models. And this has stoked some debate in the community as to whether we need to tweak the models to fix this, or whether there's some bias in the rocks that end up exhumed to the surface. So I hope that gives you a sense of how these thermal models are produced in detail. To summarize, there are several inputs needed to predict or model subduction zone thermal conditions, but the most important seems to be the thermal parameter phi, which is the convergence rate times the plate age. There's multiple ways. I just showed you a few examples to compare predicted subduction geothermal gradients to observations from the real Earth. They don't always agree, but at least they suggest that we're doing fairly well or fairly close. Next up, we'll talk about how the subduction geotherm affects metamorphism and water release and why it matters for subduction zone processes.